Hello. In this video we're going to take a look at Fourier transforms. So we have the resolution of the identity into the position basis, and we can also write it in the momentum basis instead. So these states x and p, these are form our complete orthonormal bases. They're two different bases to describe the same infinite dimensional Hilbert space. And we also have from previous video that they should be eigenstates of the position and momentum operators respectively. That is, we'd like the operators x and p acting on their respective eigenstates to return the eigenvalues x and p. So these things, remember, look a little bit tautological. Sorry, I've missed the corner of that cat. But they're different things: operator, state, eigenvalue, and the state again. Okay, so we can use this to show the following result. We have that the inner product of psi with itself must be 1, and finding this as a normalization condition on the wave function. We can do exactly the same thing. We can start with this, and we can insert instead a complete set of momentum states, and we find the following result, that 1 must also be equal to the integral over all momenta of the modulus square of the Fourier transform of the wave function. And so this relationship here, that this quantity is unchanged whether it's in x or p, is an example of what's called Parseval's theorem. So what we're saying is that x written in the position basis is the is related by Fourier transform to psi written in the position basis is related to the Fourier transform of psi written in the momentum basis. So let's look at that in a bit more detail. So we have that the kept psi projected into the position basis is the wave function psi of x. And then we can insert into this a complete set of momentum states as follows. So I've just taken this object and I've inserted this integral p outer product p into the middle between the bra and the ket. And then I've used the fact that x and in fact psi are not functions of momentum. So we can pull it out the front here. And now we see that we have p inner product psi here, which is psi twiddle of p. But now this is looking very much like a Fourier transform, rather than inverse Fourier transform. But that would be true only if x inner product p were equal to the following. E to the ipx over h bar, where because px is not dimensionless, it has the units of h bar, we should have a dimensionless quantity up here, so it's natural to put e to the ipx over h bar. And then there's a normalization on this, that 1 over square root 2 pi h bar, which is convenient, but there's this usual ambiguous choice of normalization when it comes to Fourier transforms and inverse Fourier transforms. So let's use this definition. So if we say that x inner product p is this, then we have the usual Fourier transform written here. And the Dirac notation has naturally encoded that Fourier transform in the following form. X inner product p is e to the ipx over h bar with a normalization of 1 over square root 2 pi h bar. And we can check that this is the inverse Fourier transform. The Fourier transform itself works just as well. To find p inner product psi is equal to psi twiddle p. We can insert a complete set of position states this time, and we find the following. X inner product psi is psi of x. And so this is a well-defined Fourier transform, provided that this object p inner product x is given by e to the minus ipx over h bar over square root 2 pi h bar. So this makes a usual Fourier transform, inverse Fourier transform pair with the correct normalization. And you see that what we're saying here is the following. So we've had to use the fact that p inner product x is the complex conjugate of x inner product p. That is, but this is built into the Dirac notation already, that for any vectors, if we write x inner product p, then p inner product x is the complex conjugate of that. That's part of the notation. And additionally, we're saying that x inner product p is given by this form over here. But we'd also like to say that p is an eigenstate of the momentum operator. Well, what are eigenstates of the momentum operator? They're nothing other than plane waves. So what we'd like to say is that x inner product p is a projection of the plane wave into the position basis. And that's exactly what this is. right? This is the form of a plane wave. In this case, a right-going plane wave, and in this case, a left-going plane wave, the complex conjugate. So all of this structure has worked out quite nicely and naturally in the Dirac notation. So Fourier transforms all work very well. And there's questions about this in the problem set. So just to finish up, we'll look at that in slightly more detail. So writing in the position basis, we've seen already that the momentum operator is expressed as follows. And so the claim is that the plane waves are the eigenstates of this operator. And we can check that straightforwardly by substituting. So we insert the plane wave form from the previous board, insert the form of the operator, it brings down an IP over h bar. And so we see that we have the following result. P acting on the plane wave state is equal to the eigenvalue, a real number, acting again on the plane wave state. And so then it's natural to interpret this object as the eigenstate of the momentum operator, but clearly it's written in the position basis, and so it's really this. And so that's what we saw in the previous board. Okay, so in the next video we'll take a look in a bit more detail at operators in this formalism. Thanks for your time.